There are also hypothesis tests for testing differences between two means. Now, let's say a manager is comparing two data sets that should be equivalent, but he or she wants to make sure that they are really equivalent. This is a hypothesis test of two means. If the two samples are equivalent, then the difference between the means should be zero. So let's say we have average response time for a call center in San Antonio is 5.4 seconds, and another in Morgantown, West Virginia with a response time of 5.2 seconds. Our aim is to see if the two means are the same. Or in other words, is the difference between 5.4 and 5.2 statistically the same as zero? Here are a few other examples. We want to compare the average scores of one class to another to see if they're the same. Or compare the average runs scored per game for the New York Mets versus the average runs scored per game for the Washington Nationals. We could even compare the difference in average income for a sample of people in New York City against the sample of people in Los Angeles. Now, it's important to note that when we examine differences between means, we need to recognize whether the samples are paired or independent. Paired samples are samples in which the observations or subjects are considered to be the same or from the same pool, randomly assigned. So let's take an example. Consider we have 30 students at random from one class and 30 from another. Each sample should have an appropriate representation of the class with no bias, especially if the sample is large enough. However, if we separate male and female, then each sample is different from the other in some particular way, and they behave differently. In the first case, we have what's known as a paired sample. In the second case, it's considered independent samples. And the reason for this is important because the underlying assumption for paired samples is that their variance or standard deviation will be nearly identical, because you're comparing two of the same exact populations. They're just being paired at random. However, independent samples may have a different variation to them, and we need to ensure that we account for that variability specifically. So we're going to focus on paired samples. Now, for a paired sample, we're testing the difference between the two means, and the process is quite simple and similar to the processes that we've had before. If we have two classes and we take the scores and average them, we wish to know if there's a difference in test scores between the two classes. Therefore, the difference should be zero or statistically zero. Now, we've set up all of our pieces here to the left. We have our X1 bar, which is the class average in sample 1, 85.6, the class average in sample 2, 87.5, and we take the difference between the two and obtain a value of negative 1.9. Now, D0 or D0 is actually the number that we're comparing against. Later on, we can actually compare to see if the difference between the two means is 6 or greater than 6 or less than 5, because we know that there's a difference. So this is actually one of the things that we're contrasting against. In this case, our D0 is 0 because we're testing to see if the difference between the means is equal to 0. So this is what we're comparing the difference to be. Now, our standard deviation from our sample example, it will be 11.49, and again, we would get this from the sample. Our N1 and N2, the number of observations in sample 1 and sample 2, are 30, and we set up our hypothesis test. Our H0, the null hypothesis, is that x1 bar minus x2 bar equals 0. Our alternative hypothesis is that x1 bar minus x2 bar is not equal to 0. And again, we could rephrase that a little bit by saying x1 bar minus x2 bar equals D0. So that D0, that D0, which is the difference that we're comparing to, is the right side of the equal sign in the hypothesis test. Now, how we calculate the standard deviation here is by subtracting each of the observations in one sample from the other to obtain the difference. So an example would be if we have our set of data for sample 1, our set of data for sample 2, we're going to calculate a third column that will have the difference between the two. And then what we're going to do is we're going to take that and calculate the standard deviation, and that will give us one standard deviation. So the formula that we have is our t-statistic is going to be the difference between the two sample means minus that D0. Now remember, if D0 is 0, then it would just, the numerator would be the mean of x1 minus the mean of x2, all over the standard deviation divided by the square root of n. When we do this, we end up with a value of negative 0.9061. Now what we're going to do is we're going to take that and we're going to put that into the t.distribution.2t for two-tailed test. But we're going to take the absolute value of that number. And we're going to get 0.373. You're going to notice on the right side here that we're using the t.dist.2t function, again because our hypothesis test is equals. But our t value that we got was at negative 0.9061. Now, the t.dist function will not allow you to put in a negative number. So what we're going to do is we're going to take the absolute value of that, and you should be able to recognize that whether we took the negative value or positive value won't matter, because it's going to give you the area under the curve, and since it's 2t, the two-tail, it's basically going to double the area under the curve from a particular point automatically for you. And so it's going to actually return the value of 0.373. Now, the other piece here is that the degrees of freedom is 29. And you might say, well, we have two samples, so therefore it's going to be n minus 2 degrees of freedom. Well, the thing is that remember, we had talked a little bit earlier that to calculate the standard deviation, we just took the difference between the two samples and we estimated the sample standard deviation from that. Well, that's one estimation, not two. We don't have two separate standard deviations that we're using. So that's why in this case we're doing the n minus 1 degrees of freedom as opposed to something with n minus 2. And since 3.73 is greater than the 0.05 confidence level, we cannot reject the null hypothesis, and we can state that the two sample means are the same. Now, if we have two means, but we have them from an independent samples, say where we took all male students in one sample, all female students in another, then it gets a little bit more complicated, but only because of the pool standard deviation that we need to do. So it's the standard deviation that will cause the issue. We set up our entire problem the same way. Our x1 bar is 85.6, x2 bar would be 87.5. The difference between the two samples might be negative 1.9. Again, it would be just chance that it was the exact same numbers as it was before. Our D0, our difference that we're testing against, is 0. Now, we would calculate a sample standard deviation for the first set, which is 9.2. Do the same thing for the second set, which is 8.1. And we have our N1 observations is 30, N2 observations is 30 as well. We set up our hypothesis test, x1 minus x2 bar. x1 bar minus x2 bar equals 0. Our alternative hypothesis, x1 bar minus x2 bar not equal to 0. Again, we're going to do a two-tailed test. So we can see here that the formula to the top right is generally the same, but the denominator has changed. We have a fraction on the denominator, which is the pooled standard deviation divided by the square root of 1 over n1 plus 1 over n2. This somewhat looks similar to something that we had done with the confidence interval, and the fact is that it is. The formula for the pooled standard deviation is the same. We're going to be taking the square root of the entire quantity, n1 minus 1, times the variance, so S1 squared is really the standard deviation of sample 1 squared. That's equal to the variance of sample 1. Remember that the standard deviation is the square root of the variance. So we're going to add to that n2 minus 1 times the variance of sample 2, or the standard deviation of sample 2 squared. We take that quantity, put it over n1 plus n2 minus 2. And in this example, when we do that, we end up with 8.722. When we plug those numbers back into the t statistic over here to the right, we end up with a negative 0.0562. And again, because it's negative, we're going to have to take the absolute value, and we'll put that into our t.dist.2t function, and we end up with 0.0562. This time we use 28 degrees of freedom, and we end up with a value of 0.972. And since 0.972 is greater than or equal to 0.05, we cannot reject the null hypothesis, and we can state that the two sample means are the same, and that their difference is 0.